The normal tangential coordinate system is used when the reference origin is in motion. Check out the examples here in dynamics of rigid bodies. The first example shows a block sliding along a bent rod with stations designated as A, B, C, and D. The particle's distance is described as 3t squared plus t, and we are to look for the acceleration of the block at different distances, specifically 1.25, 4, and 14 meters. With the bent rod's configuration as shown in the figure, and only the equation for displacement known, we need to differentiate to come up with the working equation for acceleration. By placing d all over dt to all terms in the equation, we get velocity, which is in the format 6t plus 1. As we are looking for acceleration, we differentiate the equation once more to have s double dot, or that is acceleration, as 6. This acceleration is the tangential component at, and the acceleration's magnitude should consist of both tangential and normal components, and this is computed through Pythagorean concept, root of at squared plus an squared, where we just figured out that a sub t is 6. The normal component, on the other hand, is solved using the formula, the square of velocity over the radius of curvature ρ. With a sub n requiring velocity and radius of curvature, we need to devise a way to find these parameters first, to solve for the magnitude of acceleration. Start by working on velocity. As we have computed, velocity is in terms of time, so we need to determine time first. From the distance equation, we can solve for time by plugging the given distances. With distance of 1.25 plugged as s in the equation, use quadratic formula to determine t, which would come out as 1/2 and negative 5/6. Since these are values for time, there would be no negative time, thus the second value is disregarded. The next parameter we should compute is the radius of curvature, ρ. From the illustration, the distance of 1.25 meters is located between stations A and B, which is a straight line, and the radius of curvature on a straight line is taken as infinity. So getting back to the equation for the normal component of acceleration, plug velocity as 6t plus 1, where t is 1/2, and this is divided by ρ, which is infinity. The equation is simplified as 0. So with acceleration as the root of the summation of the squares of tangential and normal components, that is with the values of 6 and 0, so the acceleration is taken as 6 meters per square second for the acceleration at 1.25 meters. Moving on to the next distance at 4 meters. Plug this into the s function to have time computed as 1 and negative 4 turns through quadratic formula. Again, there is not negative time, so negative 4 thirds is disregarded. For the radius of curvature, Take a look at the illustration and locate where the particle is, which is between B and C. With this location, ρ can be taken as 3 meters. Plug these values into the normal acceleration and get the square of 6 times 1 plus 1, and everything is over 3. This makes the normal acceleration as 16.33. With both acceleration components already figured out, the magnitude of acceleration at 4 meters is taken as the root of the squares of 6 and 16.33, and that is simplified as 17.4 meters per square second. For the last distance at 14 meters, take the value of t from the S equation, which turned out as 2 and negative 7/3. Just the same, disregard the negative value of time. Next is for the radius of curvature, and this is determined by placing the particle on the rod where 14 meters distance locates the particle along the curve with 5 meter radius. Plug t and ρ into the a sub n formula as the square of 6 times 2 plus 1, and everything is over 5 to get 33.8. With the tangent and normal acceleration components already determined, solve for the magnitude of acceleration by taking the root of the total of their squares. That is the root of 6 squared plus 33.8 squared to have 34.33 meters per second squared. The next example has a motorboat moving in a circular path where the radius is 50 meters. The motorboat's velocity is given as 0.2 t squared. It is required to look for the velocity and acceleration of the motorboat at time equal to 3 seconds. From the given formula, the velocity is taken by plugging 3 seconds for t, resulting to 1.8 meters per second. The acceleration will be solved using its components. Solve for the tangential coordinate by differentiating the velocity. So, by placing d all over dt on v, we get acceleration. d all over dt of 0.2 t squared is taken as 0.4 t. So at t equal to 3 seconds, we get 0.4 times 3, or that is 1.2. The normal coordinate is found using the formula v squared all over ρ. That is, the square of the velocity of 1.8 all over the radius of the curve given as 50. And a sub n is taken as 0.0648. Hence, the magnitude of the acceleration is the root of 1.20 squared plus 0.0648 squared, to get the acceleration as 1.202 meters per square second. For the third example, we have the tangential acceleration of a box given as 0.2 t, and we are to look for the magnitude of its acceleration when it reaches point B. With only the acceleration equation and illustration with distances given, we might as well integrate the equation to boil it down to displacement. So take the first integral to have the velocity of the particle as 0.2 multiplied by the integral of t, and that is t squared all over 2. This can be simplified as 0.1 t squared. Take another integral to get into displacement s, and we get 0.1 times t cubed all over 3, simplified as 0.0333 t cubed. What do we do with this equation? Check out the illustration. We can actually determine s, which starts from A and terminates at B. That is measured as 3 meters plus the distance traveled with the quarter circle with a radius of 2 meters, resulting to 6.1416 meters. Now plug this S into the equation, giving 6.1416 equal to 0.0333 t cubed, where t can be computed as 5.6922 seconds. As we are looking for the acceleration, which is the root of the squares of tangent and normal components, we proceed in identifying the tangential acceleration from the given formula, which is 0.2 times 5.6922, giving 1.1384. The normal acceleration is taken from the summation of the normal accelerations in the straight line and the normal acceleration of the curve. Again, the normal acceleration formula is the square of velocity all over rho. To get the normal acceleration of the particle as it traverses stations A to C, identify the radius of the curvature first, and this yields infinity, as the course is a straight line. Having infinity in the denominator of the equation makes it equal to 0. And the normal acceleration of the particle as it moves from station C to B, we have the square of the product of 0.1 times the square of 5.6922, and that results to 5.2492, which is also taken as the normal component of the acceleration. Finally, the magnitude of acceleration is computed as the root of the square of 1.1384 with the square of 5.2492, giving 5.3712 meters per square second.